Hey, so in this problem, I wanted to go over a couple of sample problems having to do with gases and moles. All right. The relationship that we're going to be taking advantage of here is the one where for any gas, no matter what the identity of the gas, it could be carbon dioxide, it could be oxygen, it could be helium. All right. If you have 1 mole of that gas, all right, remember, mole is a measurement of quantity. All right, it means you've got 6.02 times 10 to the 23rd, either atoms, molecules of that gas. It would occupy a volume of 22.4 liters of space if it's at standard temperature and pressure. All right, so really quick, I wanted to point out that, excuse me, you don't have to memorize that relationship. It's actually stated right here on page 1 of the reference guide that you're allowed to use. All right, it states that the volume of 1 mole of any gas at standard temperature and pressure. All right, and what that means is that it's not just the gas, it's a gas that's at a certain temperature. That temperature happens to be 0 degrees Celsius. All right, and at a certain air pressure. All right, meaning that the air pressure outside of the balloon, and I know that we haven't talked about air pressure or gas pressure yet, but we're just going to say that it's normal conditions. If you've ever listened to the weather where they talk about what the barometric pressure is, that's what we're talking about. So under normal pressures and at a temperature of 0 degrees Celsius, 1 mole, all right, which, like for example, if we're talking about a helium balloon, that would mean that there are 6.02 times 10 to the 23rd atoms of helium in that balloon. All right, that balloon would have this volume right here, 22.4 liters. All right, so we can take advantage of that by writing a couple of relationships. All right, so first question we're going to do is what, excuse me, what is the volume in liters of a 4.27 grams of carbon dioxide at STP. All right, so the first two relationships that we can write down are the same type that we can do for any chemical. All right, it doesn't have to be a gas, and it doesn't have to be at standard temperature and pressure. All right, so these right here, the first one just states how many particles a mole is. All right, and in this case, since it's a covalent compound, particles means molecules. All right, and then you're going to say how much mass that would be. All right, the third relationship that we can add is this one right here, where we're saying that 1 mole of carbon dioxide would occupy a volume of 22.4 liters. All right, and I just want to make a note about this. You can only use this relationship if you're talking about standard temperature and pressure. For example, if you took that exact same balloon and you warmed it up a little bit, all right, it would expand. It would no longer be 22.4 liters, all right? So you have to make sure that to use this relationship that you'll see this STP, where it mentions the words standard temperature and pressure. All right, so we're going to set up this the way that we always have. We're going to start with what the question provides us, which is 4.27 grams. All right, I'm going to put that in right there. And then I'm just going to use these relationships to try to get to the endpoint. All right, first thing that I can do, since I start with grams, is to use this relationship. All right, that gets me to moles. And then I'm going to look at, all right, how do I get from there to volume? All right, I'm going to use this relationship right here. And notice that I need to flip it upside down so that you get that diagonal relationship. All right, so that same concept with crossbars, where you're trying to get these diagonal relationships. You've got grams of carbon dioxide, moles of carbon dioxide, moles of carbon dioxide. That's still, it's the same process. One thing I want to call your attention to is at the end of each of these, you have to round them to the correct number of significant figures. All right, and anytime you're doing a crossbar, it's always multiplication or division. So what you're going to want to do is look at all of these numbers and see which one has the fewest number of significant figures. All right, this has got 3, this has got 4, this has got 3. All right, so the smallest number of sig figs is 3. There's actually 2 of them that have 3 sig figs. So when you get your answer from your calculator, you want to make sure that you round it at that third significant figure. All right. So the next question, it also has to do with carbon dioxide. So we're going to be able to use these same, these same relationships right here. All right, we're just going to do a different problem. All right, so we're going to start this with 3.4 liters of carbon dioxide, and it's asking us to get to moles. All right, the thing about this problem is that we can solve this with just one of these relationships, because this relationship gets us from liters of carbon dioxide to moles of carbon dioxide, and that's what the problem is asking us for. All right, notice that in this case, excuse me, the starting number only has two significant figures. And that is fewer than this number right here, so that's why we're rounding this answer to two significant figures. All right, so notice the difference between how these two answers were reported. This one's got one more digit when you report it because of the numbers that went into it. All right. In the next problem, we're talking about a different gas, helium. All right. So the thing is, part of this is going to look the same and part of it's going to be different. All right. We're talking about at standard temperature and pressure. So again, you can say that a mole of that is going to be 6.02 times 10, is going to be 22.4 liters. All right. And again, that's only something you can use if it's at standard temperature and pressure. These other two relationships are going to be true no matter what. All right. So a mole of helium is 6.02 times 10 to the 23rd atoms. All right. Notice that's different from what we were calling right here, because what you call a single unit of CO2 is a molecule. All right. Remember that's a carbon and two oxygen atoms, which are covalently bound to each other. All right. But the single unit of helium is a single helium atom, and that's why you use this word. All right. So whenever, if you're taking an assessment and you see that word particle, just change it to either atoms, molecules, or formula units, depending on the type of material that you're using. Okay. The other relationship is just to say, if you had a mole of helium, what would its mass be? We get that by just looking at the periodic table. And this formula, notice it's just one single helium atom. So it's the exact same mass, atomic mass that you see on the periodic table. All right. So the question that we had starts us with 14.09 liters of helium. We're going to start right there. And this question asks us to get to a mass. All right. And so that's going to be a two-step process. You can see that here. Taking a look at the number of sig figs, this has 4, this has 4, this one has 3. So this answer should be rounded to 3 significant figures. All right. The next problem right here just asks us how many moles we would have at STP, and it's just one step shorter. It's essentially this crossbar right here, but just without this last one relationship shown. And the reason for that is it's just asking us to get to moles. And once you put in that first relationship, notice you've got moles in the upper right corner. And that's when this thing is what the question is asking for. Your crossbar here is done. All right. So 4 sig figs, 3 sig figs. I should round this to the lesser of that. So I should round it to 3 significant figures. And that's why I report it this way right here. Okay. Hopefully that helps you. And that's it for this video.